All right, if you would get out worksheets 1 and 2 on polar graphing. Polar coordinates, just a reminder, you should have studied them in pre-cal and maybe already looked at typical polar graphs, but they're like r theta. To me, that's sort of backwards. I feel like that when I'm doing polar coordinates, I usually turn theta degrees and then walk whatever r is, but this is theta and this is r. The whole key to doing polar graphs is when you rotate an angle and go a certain distance, it's all turn and go. You actually can make this right triangle with x, y, and r. And so the whole key to this is this picture right here. You can see that x squared plus y squared can get you to the radius r squared. So to get from x, y to r theta, back and forth from rectangular to polar coordinates. In other words, there's two ways to get to this point. I could use my old rectangular coordinates xy, or I could use my really more efficient polar coordinates where I turn theta and walk out to that same point that way, which is used more often than rectangular coordinates actually. But you could always just draw yourself this little picture, remind yourself that x squared plus y squared equals r squared, and tangent theta will also give you y and x. So these are like super key things. Also, the sine of theta, we can see sine of theta is y over r, but I'm going to move my r over here and multiply. So I'm going to say r sine theta is y, and cosine theta is x over r, or r cosine theta equals x. These you can all get from the picture, and those are real key components to polar graphing. Polar graphs look really cool. So what you do is you turn and you go out a radius, you turn and you go out a radius, you turn some more and you go out a radius. And they can make really cool pictures like cardioids, or you'll see some that have like flower petals, and hopefully you studied those in pre-cal. I'll be, of course, reviewing it as we go pretty quickly. All right, so we're on worksheet 1 on polar. Convert the following to polar form. And I'll go back and forth to Desmos too. But if I'm looking at y equals 4, I'm going to convert that to polar form so I know y is r sine theta. So I'm going to say r sine theta equals 4. I know y, my y component, I can get it now in terms of r and theta, which are polar coordinates, r and theta. If you have polar coordinates, by the way, this polar coordinate might be pi over 3, 4. That means somebody's rotated pi over 3, and they've gone out 1, 2, 3, 4 radians to land at that point. So anyway, we have r sine theta equals 4, and you want to solve for r. So I could divide by sine, or call this 4 cosecant theta. Let's look at Desmos on that. I think I have it pulled up here. Let me see. All right, so if I put in r equals, instead of a y equals, I have r equals 4 cosecant, and then I need theta. I'm not sure where my theta is. Let's see, I can get it this way. There's a certain key I can push for theta, but I don't remember where it is, so I'm just going to copy this. Or right behind it, so I'm going to go 4, sorry. Wasn't supposed to take this long to do it. My keys are off. All right, so 4 cosecant theta. And you see I just get the line y equals 4. All right, the reason for that is, the reason that gave me the line y equals 4 is this. As I turn a certain number of degrees, like sine of theta, if I make a r theta chart, like if I turn pi over 4 radians, how far will I go? The cosecant of pi over 4 is square root of 2. So I'll go 4 square root of 2. So I'll go out 1, 2, however far that is. When I get to pi over 2, the sine and the cosecant of pi over 2 is 1, so I'll go up 1, 2, 3, 4. But anyways, it tells me to turn and go. With just all these points, every time I turn, I go further. That's the shortest distance, and then I go further away, and it makes this line y equals 4. But it's r equals 4 cosecant theta. All right, so that's number 1. All right, number 2. Again, using all this stuff in the box for polar coordinates. Number 2 is 3x minus 5y plus 2 equals 0. We're converting this out of xy. Should make a line. If you solve that for y, you would get a slope of 3/5. So let's see if we can get a line out of this. Okay, so we're going to use this fact that x is r cosine theta. So I have 3 times r cosine theta minus 5 times y, which is r sine theta, plus 2 equals 0. And then if I solve for r, I'm going to factor out an r, and I have 3 cosine theta minus 5 sine theta. Right here, with these r's on this side, I move the 2 over here. So r is negative 2 over 3 cosine theta minus 5 sine theta. So then if I made an r theta chart, it would be very time consuming, but what should happen is I should turn and go, turn and go, turn and go, and it actually makes this line. So let's look at that. So if I type in negative 2 over 3 cosine theta, which I've got to figure out how to get a theta into my Desmos. I still didn't feel like I could copy and paste, and I don't see a theta key. Let's see, do I have theta here? I feel silly that I should know this already. Gotta get my theta, and I don't see it. And it wouldn't let me copy it on this iPad. But there's got to be a way to get theta. Let me see again if I can copy. It's not letting me copy either. Alright, so let's go to Desmos on here. We'll move this down. And go to Desmos. And we'll go to Polar. Have to get into a special polar coordinates. Ought to be able to type it in now into here. Let's see if I can copy this theta here. Okay, so I can do it here. Alright, so I have negative 2. By the way, you can put your calculator in polar mode. You don't really ever need to for the AP exam, sort of like I've talked to you about parametric, but you could. Alright, so what was my answer here? I had negative 2 over 3 cosine theta minus 5 sine theta, I think. Let me move my reflection down. 3 cosine theta. Oops, sorry. Get down here. 3 cosine theta. And I think it was minus 5 sine theta. And look, interestingly enough, I get this line, and that should also be the same thing as the line 3x minus 5y plus 2 equals 0. So I'd get those same points. But what's happening here is if you actually fill in 0, you get the y-intercept. And as you keep going, you turn and go, and the points line up, kind of like I showed you a second ago. Let's get our reflection back up. All right, so now let's go to this. All right, so number 3. Number 3 is x squared plus y squared equals 25. Remember from our picture of x and y coordinates, as opposed to r and theta, which are polar coordinates, we know that x squared plus y squared equals r squared. Oh, sorry. X squared plus y squared equals r squared is one of our facts that we have here. So I can immediately go to r squared equals 25, square root that, and you can just say 5. You don't really need to say negative 5. But what that does is it draws this circle in polar coordinates, because it tells you no matter what your angle is, you're going to radiate 5. The reason it doesn't matter if you say plus or minus 5, a negative radius means that you've turned a certain amount, and then you've gone backwards 5, so you're still going to land on that circle whether you turn and go this way or turn and go that way. So number 3 is r equals 5. All right, number 4. Convert to rectangular form. So I have r equals 3 secant theta. Secant reminds me of cosine, so I can divide both sides by secant, which will give me r cosine theta equals 3. And we have these two facts about x and y to get back to x and y. By the way, we use these two statements to go to r and theta. Tangent of theta is y over x. That takes us to r and theta. To get back to x and y, we have sine theta is y over r. So we get r sine theta equals y, and r cosine theta equals x. Real important. R cosine theta is x, so we get x is equal to 3. And if I went and typed this into Desmos, you can try it. You would actually see in Desmos in polar coordinates, as you turn theta and go r, turn theta and go r, turn theta and go r, you'll get the line x equals 3. It's really cool. All right, number 4. Oh, that was 4. Number 5. Number 5 is r is equal to 2 sine theta. All right, now that one already has sine in it. And so I really, what you normally want to do is get the trig word over here with the r, but I only want r to have sine theta or cosine theta next to it. And so I really is not going to help any to divide by sine right now. So when it's written like this with the sine or cosine on this side, you introduce an r to both sides. And that gives me r squared, which is x squared plus y squared, equals 2. R sine theta is x. So if you know about conic sections, that gives me a circle that's not centered at 0, 0. It's centered somewhere else. In fact, it's probably important to look at this one. So I'm going to type it in polar coordinates. R equals 2 sine theta, but you'll see a circle that's moved over, which I'll talk about a little bit in typical graphs. Let me see if I can move this. So r equals 2 sine theta. Move this out of the way and we'll see a circle. Before I move it, let's talk about what's going to happen here. If I said 2 cosine theta, the circle would be on the x-axis, but 2 sine theta, the circle's going to be more up here on the y-axis with a radius, with really a diameter of 2, 1, 2. And so what happened was it made this circle right here. If I do 2 cosine theta, it's going to make a circle over there. If I do negative 2 cosine theta, it'll flip it over. Cosine, you know, is like x over r. And so what if I do negative 2 sine theta? Now don't get confused about the radius and the diameter. This r means how far you're going to radiate out from different angles. And so the furthest it radiated out was 2. So anyway, you should review your typical polar graphs. All right, now that was number. So when you have sine on the other side, you introduce an r. Okay, so now if I go to number 6. And I think I'd given you some polar on your summer work. All right, so that we can still look at this. Here's number 6. 6 is theta equals 5 pi over 6. All right, so this is a polar graph. If you have theta equals, put tangent. If you have r equals, try to get it with a sine or a cosine. If you have a theta equals, that means you don't even care what r is. Your just angle is going to be 5 pi over 6. So it's going to make a line, because what happens is if I have theta is 5 pi over 6, which rotates around to here, and I'm pointing this way, like I'm turning this way, and I'm going to walk however far I want to, because it doesn't have an r in it. I can walk forwards or backwards. So when I type this in, I ought to see this line right here. But to solve it into rectangular form, convert it, I'm going to put tan in front of both sides. I'm using this fact right here. I know tangent's y over x. The tangent of 5 pi over 6 is negative root 3 over 3. So I get y equals negative root 3 over 3x, which makes sense with what I said. Let's look at it, even though it's kind of cumbersome with this. Oh, I can't do a theta equals, sorry. I can't do a theta equals because all you can do is an r equal in Desmos, but I think I explained that pretty well anyway. All right, now we're finding derivatives. Okay, so how do you find a derivative if you have an r and a theta, if you have polar coordinates? I think you would agree that if I want to find dy over dx, oh, I'm sorry, I was thinking about something else for a minute. Going back to some other notes, just a second. Right, so it's sort of like parametric. You're going to have, I was getting another example out, dy d theta over dx d theta. All right, now that doesn't do really any good if I've got r's and thetas. But remember this key component that I had on the other slide, that r sine theta gives us y, and r cosine theta gives us x. So I'm going to take this fact, and I'm going to say dy d theta to get this. All right, so you know y is r sine theta. I'll keep saying that over and over again. It's based on this. This is x, y, r. This is theta. Sine of theta is y over r. So I have r sine theta equals y. By the same way, I have r cosine theta equals x. So to find dy d theta, I'm going to use the product rule, and it's with respect to theta. So I'm going to say first times derivative of the second. The derivative of sine theta is cosine theta. And then I'm going to say plus the second, which is sine theta. And the derivative of r is 1, but that's a dr d theta. This one was in the front. The reason I didn't say that was a d theta d theta. Then I'm going to put that over dx d theta. And so that's going to be first times derivative of the second plus the second times derivative of the first, which is dr d theta, using implicit differentiation with respect to theta. That'll happen every time that you want dy over dx, dy d theta over dx d theta. But you have enough to memorize. I suggest you just develop it from these facts that you're armed with right here. Okay, so And by the way, to continue taking derivatives, you need to remember to keep dividing by dx d theta, but I'll show you that as we go. All right, so don't just say dy d theta. You've got to have dy d theta over dx d theta. So let's erase this. And develop it again up high, and we can just keep using it for problems. All right, so if I want dy dx, it's dy d theta over dx d theta. And using the product rule again real quickly, you would have first times derivative of the second plus the second times derivative of the first. Then on the bottom you would have dx d theta. That's going to be negative r sine theta plus the second cosine theta times derivative of the first, which is dr d theta. All right, so now we're back to number 7. All right, so 7, we have r is equal to 2 plus 3 sine theta. And we want to find dy dx at theta equals 3 pi over 2. All right, now let's talk about what this is going to make. Again, a review, I hope, of what you learned on polar. If I start to put numbers in here, like if I make these both a 2, I'm going to get the cardioid. And I can adjust like the cardioid. That one's going on the y-axis and it's going down because of the minus. I can put in cosine. And it'll make it go negative on the x-axis. I can make it go positive. That's a cardioid. Eventually we're going to find the area enclosed in here, which you can really see here makes little sectors, but I'll come back to that. Instead of adding rectangles in a little while, we'll add up sectors. What happens if the number in the front is bigger than the number in the back? Like this, it'll make kind of a flattened out loop. If the number in the front is smaller than the number in the back, it'll make this really loop-de-loop thing. So right now what we have is 2 plus 3 sine theta. As soon as I put in sine, I know it's going to go up and down like this and have a loop. All right, now at 3 pi over 2, if you're going to be on this graph and you're going to turn 3 pi over 2, we're talking about the slope of the tangent line at 3 pi over 2. We'll see what we get, and then we'll come back to this graph. So this makes kind of a cardioid with a loop in it. All right, I'm going to need dr d theta. So first step you'll do is find dr d theta. The derivative of r is 0. The derivative of 3 sine theta is 3 cosine theta. So you needed that. Now let's fill it in up here. So I have r, which is 2 plus 3 sine theta times cosine theta plus sine theta times dr d theta, which is 2 plus 3 sine theta, over negative r, which is 2 plus 3 sine theta plus cosine theta dr d theta, 2 plus 3 sine theta. Now I need the derivative dy over dx at theta equals 3 pi over 2. So I'll probably, if I was on free response, I would take another line to do this, but everywhere there's a theta, I'm going to go back and put in 3 pi over 2. I'm not going to try to simplify all of that. So this is 2 plus 3 sine theta, which is 3 pi over 2, So I'm going to say it again as I go. Sorry, that's really messy. All right, so every time I hit a theta, I'm going to put in 3 pi over 2. So I'm going to have r, which is 2 plus 3 sine theta times cosine theta plus sine theta dr d theta was 3 cosine theta. Well, let me put in 3 pi over 2 as I go. Sine theta times dr d theta is 3 cosine theta over negative r. R is 2 plus 3 sine theta. Sine theta, sine 3 pi over 2, plus cosine theta, cosine 3 pi over 2, times dr d theta, which is 3 cosine of 3 pi over 2. All right, the sine of 3 pi over 2 is negative 1, and the cosine of 3 pi over 2 is 0 as we're going. All right, so in the front, I have 2 plus sine of 3 pi over 2 is negative 1, so I get 2 plus negative 3, times the cosine of 3 pi over 2, which is 0, so that goes away anyway. Then I get the sine of 3 pi over 2, which is 1, negative 1, times 3 cosine of 3 pi over 2, which is 0. So the entire top just went to 0. All right, on the bottom, let's see what I get. On the bottom, I get negative 2 plus 3, so that's negative 1. The sine of 3 pi over 2 is negative 1. And then this is going to be all 0. So it's important that it gets 0 over a number and not 0 over 0. So it looks like I'm getting 0 over 1. All right, so my slope is 0. Now, if I look back at the picture of, I had that cardioid that was going like this. Well, it was really a loop in it that went like this. And at 3 pi over 2, you can see that the slope should be 0 at 3 pi over 2. I don't know if I can show you that point or not. Like it's not letting me click on that point at 3 pi over 2. You get this point right here, and you have a horizontal tangent. All right, so your first experience in taking derivative in polar coordinates. So you're going to have dy d theta over dx d theta. And I wouldn't memorize what happens. I would just derive that big thing every time. It's not that bad. It looks really bad, but it's not that bad. Okay, so sorry, to get it hooked up to power. All right, so number 8. Going on to number 8, I think I will erase all of this once I have it down. And we'll do number 8, using all of our facts. So I still have my kind of ugly looking derivative there. Alright, so for number 8, we have r equals 3 times 1 minus cosine theta, which gives me 3 minus 3 cosine theta, which, if you wanted to know what it looked like, it would be, since the 3's are the same, it would be a cardioid, and the negative's going to pull it along the x-axis. It would look sort of like this if you type it into your calculator. A cardioid is if these are exactly the same number. And we're doing the equation of the tangent line of theta equals pi over 2. So you ought to get something like this. Because if we're looking up, if we're turning our angle at pi over 2, we're landing somewhere like that. Okay, so I'm going to fill it into here. Oh, but first I'm going to need dr d theta for my formula right here. Dr d theta is at the end of both of those using the power rule. Remember, we took dy d theta and dx d theta. All right, dr d theta, the derivative of that is, derivative of 3 is 0, and the derivative of this is 3 sine theta. So I'll need that. All right, so I'm going to say r, which is right here, 3 minus 3 cosine theta times cosine theta. I'm going to erase this, but remember that picture that I predicted. Plus sine theta, dr d theta is 3 sine theta over negative r, which is 3 minus 3 cosine theta times sine theta plus cosine theta, dr d theta is 3 sine theta. Hope I got all that right. I'm going to put in pi over 2. Everywhere there's a theta. So this is the derivative at pi over 2. Remember, all of this is really just dy d theta over dx d theta. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. So this goes to 0, so I have a 3. Cosine of pi over 2 is 0, so that goes away. Sine of pi over 2 is 1, and this would be 3. Over negative. Cosine of pi over 2 is 0, so I get 3. The sine of pi over 2 is 1, and this goes off to 0. So I get a slope of negative 1. If you remember my picture, it looked like this. And at pi over 2, I'm not surprised that my slope of my tangent line is negative 1. All right, let's go, if we can, to number 9. So to derive it again, dy dx is dy d theta over dx d theta using this. Y is r sine theta, x is r cosine theta. So dy d theta was first times derivative of the second plus the second times derivative of the first. I do this every time. Dx d theta is first times derivative of the second plus the second times derivative of the first. I'm going to fill into that for number 9. Number 9 is r equals 4 sine theta. I keep talking about what these make. 4 sine theta. Sine is going to be on the y-axis. And for instance, if you fill in pi over 2, you get 1, 2, 3, 4. I'm going to make just a circle that goes like this. So anyway, I'm going to need dr d theta in my problem. So that's going to give me 4 cosine theta. All right, so I'm going to say r, which is 4 sine theta, cosine theta, plus sine theta, dr d theta. Dr d theta is 4 cosine theta over, and you should announce what you're doing, dy over dx, is negative r, which is 4 sine theta. I couldn't do this, I would definitely want to write that down and look at it. Wouldn't want to do it from memory. Sine theta plus cosine theta, dr d theta is 4 cosine theta. And number 9, we're doing this at pi over 3. I'm going to put in pi over 3 pi over 3, pi over 3. Everywhere there was a theta. Okay. The sine of pi over 3 is root 3 over 2, and the cosine of pi over 3 is 1/2. So to get started, I have 4 times root 3 over 2, sine of 60 degrees, cosine is 1/2, plus sine of pi over 3 square root of 3 over 2 times 4 times 1/2. On the bottom I get negative 4. Sine of pi over 3 is root 3 over 2, root 3 over 2, plus the cosine of pi over 3 is 1/2 times 4 times 1/2. Be careful through all this. So these cancel, and I get root 3. These cancel, and I get root 3. And these cancel, and I get negative 3. And these all cancel, and I get plus 1. So I get 2 root 3 over negative 2. And so for my slope, I get negative root 3. All right, now to see what's going on there, if I rotate pi over 3, I'm going about right here. And the slope looks like it should be negative about 1.732. So that makes good sense. All right, let's go to number 10. I'll do it on here so I can look back at my derivative pattern. All right, so number 10. 10 is r sine 3 theta. R equals 2 sine 3 theta, and theta is pi over 4. All right, what would this look like if I put it in Desmos? It's going to be one of those, they call them roses, looks more like a daisy to me. If you have the 3, you would end up with 3 petals. It looks sort of like this, I think. If you have an even number, you get twice as many petals. And the radius, that the biggest point would go out 2 units, would be the tip of those petals. So let's look at that real quickly. So we have r equals 2 sine. Now all of a sudden, if I've got a 3 in front of here, it's going to do some different things. So I have 2 sine 3 theta. And so I get this, what they call a rose, the mixed flower. Okay, and eventually we're going to find the area enclosed in here, just a heads up, the area of the petal. All right, so let's go to, okay, we're doing this at pi over 4. All right, so let's go to our prototype here, to our pattern. So dy over dx is r cosine theta. R is 2 sine 3 theta is pi over 4 times cosine theta is pi over 4 plus sine theta pi over 4. And I haven't found dr d theta yet. If I did that, dr d theta would be 2 cosine 3 theta times 3, so 6 cosine theta. 6 cosine 3 theta is dr d theta, which I need right here. So I have 6 cosine of 3 pi over 4 over negative r, which is 2 sine 3 theta times sine theta, sine of pi over 4, plus cosine of theta, and then dr d theta was 6 cosine 3 theta. This is patterned every single time, but I derive it every single time. Or I derive it once at the top of the worksheet and use it over and over again after I get used to it. Right, the sine of 3 pi over 4 would be root 2 over 2. The cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2 times 6. The cosine of 3 pi over 4 is negative root 2 over 2. On the bottom I get negative 2. The sine of 3 pi over 4 is root 2 over 2. Root 2 over 2. Cosine of pi over 4 is root 2 over 2. 6. And the cosine of 3 pi over 4 is negative root 2 over 2 in the second quadrant. Alright, these cancel, and I get 2 over 2, which is 1. Alright, these, the square root of 2 times the square root of 2 is 2. And it looks like I get negative 3 there. You've got to be really careful. Square root of 2 and square root of 2 gives me 2. And these cancel, so I get negative 1. Square root of 2 and square root of 2, by the way, there's a minus sign here. And I think I get minus 3. So it looks like I get negative 2 over negative 4, which is a slope of 1/2. Now look at where I've turned to make sense of this. Turned at pi over 4. And so I'm not sure where pi over 4 is, somewhere like this. And the slope is 1/2. It's probably further down here like this, where the slope is 1/2. If I did a better graph of it on color graphing paper. Okay, so that was number 10. Number 11, be very literal. Remember that word that I've gone back to that you can barely read right there, be very literal. Alright, so it says find horizontal and vertical points of tangency for r equals 1 plus sine theta. In our experience, we know we're going to need dr d theta, so that's cosine theta. Alright, now I'm going to find dy dx based on x is r cosine theta and y is r sine theta. So dy dx, to derive it once again, is dy d theta first times derivative of the second, sine theta, plus the second times derivative of the first, which is dr d theta, over dx d theta, which is first, probably shouldn't be doing it this crazily, so let's start over. Dy d theta, I may be doing that wrong. Dy d theta is first, comes derivative of the second, plus the second comes derivative of the first. And then dx d theta is first, comes derivative of the second, plus the second comes derivative of the first. So dy dx is r, which is 1 plus sine theta, cosine theta, plus sine theta, dr d theta is cosine theta, over negative r, which is 1 plus sine theta, and sine theta plus cosine theta, dr d theta is cosine theta. Now how do we let's start off with horizontal tangency. How do we find a horizontal tangent? The derivative would have to equal 0. So we want dy over dx, we want the numerator to be 0. So I'm going to set this part equal to 0. So I'm going to say, in red here where you can see it, I'm going to say 1 plus sine theta times cosine theta plus sine theta cosine theta. Where does that equal 0? That's what I'm looking at for my horizontal points of tangency. So when I distribute, that will give me cosine theta plus sine theta cosine theta, and another 2 sine theta cosine theta equals 0. Factor out a cosine theta, 1 plus 2 sine theta. Set those equal to 0, where does cosine theta equal 0? And this would give you where does sine theta equal negative 1 half. Right, cosine theta equals 0 at pi over 2 and 3 pi over 2. Sine is negative 1 half at 7 pi over 6 and 11 pi over 6. You have to be really careful here, though, that it also doesn't make the bottom 0. I don't want 0 over 0, I want only 0 on the top. And so at 3 pi over 2, I crossed it out, and I'll show you why in just a minute. But at 3 pi over 2, it makes it 0 over 0, which we'll see in just a second. So now I know I have horizontal tangents at pi over 2, 7 pi over 6, and 11 pi over 6. The question is, I think it wanted points. Points. So now I want points. So this is theta, I need r. So I fill them in to here. And so I have a horizontal tangent, r theta at pi over 2. When I fill in pi over 2 here, I get 1 plus 1, I get 2. I'm going to draw a picture of this in a minute. When I fill in 7 pi over 6, I get 1 minus 1 half. So I get 1 half 7 pi over 6. And the same thing for 11 pi over 6. Okay. So what this is I'm going to draw a little bitty picture of this up here if I can. This is a little cardioid, 1 plus 1 sine theta. Should be going up like this. And so I have horizontal tangents at pi over 2, 2. And then at 7 pi over 6, if I rotate around 7 pi over 6 and go out half a unit, or if I rotate all the way around 11 pi over 6 and go half a unit. I have horizontal tangents at all of those places on that cardioid. Traveling here, here, and here. Now let's imagine where the vertical tangents would happen, and we'll talk about that. So vertical tangents, so I'm going to leave my horizontal note right here. And so that we can look at my work, I'm going to erase up here. I'm going to look at what gives me the vertical tangent. It's all tedious, but very doable. So for a vertical tangent, I want it to be undefined, so I want the bottom to be 0. But I don't want I want the bottom to be 0, so I want it to be undefined. And so I'm going to say negative 1 plus the sine of theta times the sine of theta plus the cosine of theta times the cosine of theta. I want that to equal 0. That gives me negative sine theta minus sine squared theta plus cosine squared theta equals 0. That's not sine squared plus cosine squared. Since this is negative, I'm going to get it all in terms of sine. So I get negative sine theta minus sine squared theta plus cosine squared is 1 minus sine squared. So I get 1 minus, get this in red where you can see where I'm working. So I get 1 minus sine theta minus 2 sine squared theta equals 0. Since I've used this already, I'm going to erase a little bit more from my vertical tangent. So now I'm going to factor this. I get 1 times 1, 2 sine theta times sine theta minus plus. So I get, it has a vertical tangent where sine theta is 1/2, which happens when my angle is pi over 6 and 5 pi over 6. And I get where sine theta equals negative 1, which happens at 3 pi over 2. But remember my numerator was also 0 at 3 pi over 2. I have to throw this one out because it makes the top 0 and the bottom 0. I don't want 0 over 0. I want just 0 on the bottom to make a vertical tangent instead of a hole in the graph. So I'll point at this continuity. So based on this picture, these vertical tangents are happening there. And to actually find the point, I fill them in. And so I'm going to have r theta and r theta, 5 pi over 6. So if I put in pi over 6, I get 1 1/2 or 3 halves. And also on the bottom, I'll get 5 pi over 6 is positive. And so what happens is on this axis, if I rotate 30 degrees or pi over 6, and I go out 1 1/2, I get a vertical tangent. And if I rotate over there, I get a vertical tangent. Okay, so that was number 10. That was good, number 11. So the last one on worksheet 1 is number 12. All right, so number 12 is given the polar graph, the polar curve r equals theta plus sine 2 theta, which, by the way, I don't know what that looks like, so we'll talk about that. That's not one that you should know, but be sure that you're careful in your domain. And it says sketch a graph of the curve. All right, so let's see what happens here if I'm doing r and theta. Okay, it says use your calculator on problem 12. So it's a little unusual to have to put your calculator in polar mode, but you might want to try it. You can go into polar mode and do the graph. And you'll get a picture that looks like this. If you go into polar mode and go to your whiteboard, you'll get an r equals and your x becomes a theta. Alright, but it's a really weird looking graph. Theta plus sine 2 theta. So you get this really weird graph, but we're only graphing it on your window on your calculator. You're only going from 0 to pi. And so you get this weird looking little graph here, and you just copy it onto your paper. So looks like this. By the way, if you did an r theta chart, if you put in 0, all of this goes to 0. If you put in something like pi over 2, you get pi over 2 plus the sine of 2 pi over 2, which is 0, so you get pi over 2. So up here, you go up about 1.5. Anyway, if you had to, you could probably find points. It stretches through here, and then winds around like this, and ends at -3. Try to draw like more of a graph like what you saw. This one's pretty bad. Sorry. Alright, find an angle theta that corresponds to the point on the curve where x equals -2. Alright, go back to our facts that we have right here. This is x, y, r, and theta. We know that cosine of theta was adjacent of our hypotenuse x over r, so x is r cosine theta. So where x equals -2, I'm going to have x is r cosine theta to get into polar coordinates. And so now I know r. I can sub it in as theta plus sine 2 theta times cosine theta. And I want to know where that equals -2. And so I put all of that into my calculator, which you can actually do even in function mode. You could type it in as x plus sine of 2x times cosine of x equals -2. And do calc intersect. You really don't need polar mode, and you get 2.786. C, you want to know where y equals 1. All right, we knew that our sine theta is y, and so y is r sine theta equals 1, and r was theta plus sine 2 theta. Again, you can use your function mode and do x right here. You can put in a, sorry, you can put in an x for theta and just do function mode. Calc intersect, try it. And you get two answers where theta is 0.661 and 2.223. This is 0.661. All right, and then it says D, for what values of theta is dr d theta positive, and what does this say about the radius, and what does it say about the curve? Okay, so again, be very literal and do what they say. We had an x equals, we had a y equals, and so we use this fact along with our given r. All right, but now they ask me to find dr d theta, not dy dx, dr d theta. So let's go up here and find dr d theta. So it's the derivative of r with respect to theta. So the derivative of theta with respect to theta is 1. The derivative of sine 2 theta is cosine 2 theta times 2, and this is also with respect to theta. So now I'm going to do a plus minus chart. I'm going to look at where this equals 0 to find my critical numbers. And so you could actually do this by hand or put it in your calculator in function mode. But I'm going to go 2 cosine 2 theta equals -1. Cosine 2 theta equals -1/2. I'm looking at that as cosine u equals -1/2. Briefly letting 2 theta be u. Cosine is -1/2 at 2 pi over 3 and at 4 pi over 3. And since it says 2 theta, I should go around twice. So I'm going to add another rotation to that, and that's going to take me 6 pi over 3 more, 8 pi over 3, and 10 pi over 3. Then I take u back out and put 2 theta back in. So I divide those all by 2. If I divide this by 2, I get half of that, which is pi over 3. I get half of that, which is 2 pi over 3. And when I take half of this, I get 4 pi over 3. And half of that, I get 5 pi over 3. But look at my domain, it's only 0 to pi. See? So these are past pi. I don't need these two. So these are the ones I take into account as my critical numbers. Why am I doing critical numbers? I want to know where the derivative is positive. So from 0 to pi, I'm looking at pi over 3 and 2 pi over 3 out to pi. And we think this is a calculator active problem, so you could actually look at a graph of the derivative and see what the signs are. Or you could fill in numbers like pi over 6 and figure it out. But it goes plus, minus, plus. And so it's positive on the interval from 0 to pi over 3. And it's also positive again on the interval from 2 pi over 3 to pi. So what does that tell me about the radius? This is a change in radius. So it tells me that the drd theta is positive during those times. I wish I had more room up here, so let me erase and I'll write up here. Right, so answering still the d pi. What does that tell me about the radius? It tells me that the radius is increasing on these intervals. I'd probably name again the radius is increasing from 0 to pi over 3 and 2 pi over 3 to pi, and that tells me about the curve. What does that tell me about the curve? If the radius is increasing as I go, that means the curve is getting further away from the origin. If my radius dr d theta is positive, I'm getting further away, and then you see for a while I'm getting closer, and then it stretches out to further away. The curve is getting further away from the origin. During those times. All right, so what should be happening from pi over 3 to 2 pi over 3? For a little bit of time, they're getting closer, and then it's weirdo graph. It's getting further away.